We are going to take a look at polar graphs, taking polar equations and graphing those onto a plane. In the past, you've done a lot of graphing using x's and y's, and that would be on the Cartesian grid. Okay, so just as rectangular equations describe the relationship between x's and y's on a Cartesian grid, so when you graph them, you guys are used to all that stuff with the x's and the y's. What we're going to be doing is graphing pretty similar equations, but instead of using the x and the y, what we're going to be doing is using an r value and a theta. Now, oddly, I should point out here that the theta, which seems to be in the y position, that will actually be the input to any of this graphing, and then the r value, which seems to be in the spot where x would be, that would actually be the output. And your equations will look sort of like this. You'll have r equals and then something that involves theta. Our approach to graphing here is going to be very elementary. And what that means is that we're going to take an equation that we have, we're going to build a table of values. We're going to build a table of values, most likely up to 2 pi, but sometimes you only need to go as far as like maybe pi. Okay, so we'll build a table of values, and then we'll start to plot all those coordinates that we have. So all of our thetas, we're going to plot those, and then once we have enough of them, we'll just go ahead and start to connect all of the points in a smooth curve, which will ultimately create the types of graphs that we want to look at here. All right, let's go ahead and take a look at the graph of r equals cosine theta. All right, now what I want to do first, just to make a point here, is that we're going to be graphing on a polar coordinate system, which is, of course, different than the xy coordinate system. So you've seen an equation like this before, but we would have written it as y equals cosine x. So it's not really much different, right? We would still be inputting angle measurements into the cosine and then getting responses back on that. And that graph, which would have been in the rectangular form, would look like this. It would be that wavy graph that we see. All right, so the graph that we're going to get in the polar system is not going to be the same thing, even though the equation is pretty much, the same idea. We're going to be putting angle measurements into the cosine, into theta, and we're going to get the same answers back that we would have when we made that curved graph, except that the way that we plot these, your angle measurements are not going to be measured along the x-axis in that direction. Okay, your angle measurement is going to be measured as you rotate around. Okay, so we're not building the graph that way, we're actually building the graph in a circular form that way. And then the radius, instead of like our other equation where the y values would tell you how high up you go, the radius is going to indicate how far you extend from the origin. Not how far you are from the x-axis, but how far you would be from the origin. So we're going to end up getting a completely different looking graph than what we had there. All right, to start things off, I went ahead and already completed a table. That way you wouldn't need to go through the whole process of doing this. However, you could verify some things here, right? In cosine, add 0 degrees, or 0 radians, these are all in radians actually. Add 0 radians, you do get 1. That's a high point. In fact, I'll show you this graph again here because it tells us that at 0, we get 1. All right, other things that we see at pi, we get -1. That would be this point. Okay, and then right between those at pi over 2, that would be a 0, which is here. Okay, so all these have been filled in. These have all been filled in. I want to make one additional point right here. This is the best rounded value that I decided to put here, but if you were to really evaluate the cosine for pi over 6, that would actually be, it would be 0.866. It would be the square root of 3 divided by 2. Okay, so that one's been rounded up just a little bit, up to 0.9. All right, so here's how we graph, a tedious process, okay, but this is going to be our approach at all the graphs that we do here. All right, so at 0 degrees, which would be here, at 0 degrees, we get a radius of 1. Okay, so I'm going to put a point there. At 0 degrees, we get at 1. Okay, pi over 6, we're going to get 0.9, so a little bit short of 1. It was actually the 0.866. Pi over 6, I recall the whole thing is pi. I've got 1, 2, 3, 4, 5, 6, which means I get 12 increments, so pi over 6 is going to be 2 of those increments. That would be here, and then I'll go ahead and mark off pi over 3, because that would be right here. That way we don't have to do it later, and we'll do a couple more, I guess. 2 pi over 3, And 5 pi over 6 will be over here. 5 pi over 6. Go ahead and just get those thrown in there. So that would be a 12th. We don't have any that are divided by 12 here. All right, so at this line right here, we're gonna have a distance of 0.9. Okay, so I gotta do the best that I can to estimate. I do have these broken into fifths here, right? 1, 2, 3, 4, 5. Okay, so each of those is a fifth, which is about 0.2. So that would put us at 0.8. That'd be 0.8 and then getting up to there. So it's about halfway between those two, okay? Next, pi over 3 is gonna be at 0.5. Okay, so that'd be here, and then this would be 0.5. It'd be 1, 2.5 little rings there. All right, what else do we got here? At pi over 2, which is going to be the vertical here, that would be 0. We're actually at the origin for that one. And then over here, this will be a bit interesting. We get a negative 0.5. So instead of going out 0.5 here, we're going to need to follow that back in to here. It's actually going to be directly below that point that I had. All right, then what do we got next? 5 pi over 6. That would be here, but we're going to follow it through, and that is at a negative. We're following that through because it's a negative, so it's a 0.9. That one is actually going to be directly below this point here. It's going to be in that spot. All right, so it sort of looks, based on what we've got so far, that if we connect it with straight lines, we would just get a hexagon that'd go around, but it's actually going to be a curved type graph that we have here. All right, so the others here, at pi, we get -1. So at pi, we're going to get -1. So that actually just puts you right back to the spot where we were at. Over here, you're going to get at 7 pi over 6. That would be on this line here. 7 pi over 6, you're going to get a negative 0.9. So if you follow that through, let's get on the right line here. All right, you follow that through, it will end up actually being in the same spot. So the rest of these are actually just duplicates of everything that we would have seen there. All right, so if we were to connect these with a smooth curve going around, what shape do you think that would look like? What do you think that would look like? All right, let's see if I can make a graph on the calculator here efficiently. What I need to do first is I got to change this from a function which thinks of things as x's and y's. I have to change it to polar. Got to go there, and then if I go to y equals, you're going to notice that it actually says r equals. That all of these are going to be r equals. So I've already got sine theta in there, but I'm going to be graphing cosine theta. So if you press the X button, it just pops up as theta, which is pretty neat, so it knows to do that. In addition, before I graph it, what I'm going to do is try and set a window. I'm going to try and get a good looking window of like the space that I have here. So I'll go to the window to set things up. You get to choose your theta. What we did is go all the way from 0 to 2 pi. So actually that is 2 pi there, but I'll just type it in so you can see it changes into a decimal. The step, don't worry about that stuff. The X minimum, so now this is going to talk about our window size. We went, it was a big window, but we did -2 to 2, so -2 to 2, and we did the same thing for the Y values. All right, now when I graph this though, because the screen that I have is a rectangle, it's going to look a little bit compressed, and then after I graph it, I'll square it up, because it does have a feature for that. All right, so let's see if this works. Let's see what it looks like when we do a smooth curve connecting each of these together. Looks like that. All right, so it looks like an ellipse. Okay, but remember, our screen is a rectangle, so it's actually been squished. If I go to zoom, and I tell the calculator to square things up like balance for the shape of the screen that we have here, to balance things out, we will actually get a circle. This actually ends up just being the graph of a circle. All right, and the period that all we'd really need to draw the graph would only go up to pi. Everything after that is actually just going to keep cycling through the same values over and over again. All right, so let's see if I can actually draw a circle on this. It's a bit small here, so it might be a little bit hard, but The center of the circle would be here, so I'm going to mark that off for reference. I'm going to take a compass. I'm going to center it, and like this is about the smallest that I can set this at here. All right, let's see. We're going to maybe miss a couple of the points here, but try. Not too bad. That's about as good as I'm ever going to be able to do that graph. So there you are. That is a circle, which is the graph of r equals cosine theta in a polar grid. Okay, remember in a rectangular grid, it's that waving graph. All right, so let's go ahead and take a look at the graph y equals sine theta. Okay, so all we've done here is we've changed cosine to theta. And you might be able to predict what this graph will generally look like, but then the differences would be just sort of unknown because this is a brand new topic that we're looking at here. And the reason that you might be able to predict what it looks like is because when we did these in rectangular form, the graph of sine and cosine are pretty much the same graph, except just offset by 90 degrees. That was literally the only difference with them. So, sort of keeping that in mind, you can probably guess what this graph will look like without knowing the little details. All right, so I already got the table prepared for us. At theta as 0, the r value is 0, so the sine of 0 is 0. Okay, so that's going to give us a point right there at the origin to start things off. At pi over 6, again, this was pi over 6. At pi over 6, we're going to get 0.5. So that's going to be here. Okay, and then at pi over 3, which is here, you're going to get that 0.9 value, the one that's a little bit hard to estimate, but it's about there. And here we're going to get 0.5. So all these are positive so far. That's pretty good. Let's make sure I'm on the right side. 1, 2, and then a half. There we are. And be at that spot. All right, and then look, at pi we're back to 0. So you're starting to see that like hexagon shape happening again. And then as you go through the rest of these, they are going to end up just matching like the same places. Here's a really easy one at a 3 pi over 2, which would be this direction. You actually have -1, which will take you up to that point here. So what are we going to get? We're going to get a circle. We're going to get a circle that is centered here. All right, let's see if I can do this with my compass again. These are tough, man. These are tough here. All right, I missed that one just a little bit there, and that one in that spot. So it might have been slightly offset here, but you can see the shape of that circle that would be showing up. And on the calculator, let's go ahead and just type this one in. We'll keep the cosine in there. That might be neat to see them together. All right, so there they are. Both of these are going to create circles, except that the cosine is going to sit over here, sort of in quadrant 1 and 2. Not that we're actually in rectangular form, but you know, it's on that side. The sine graph is going to be placed on top. All right, so what we want to do next is predict what these graphs will end up doing. Okay, what happens when we get negative sine theta or 2 cosine theta? All right, now cosine theta, you know that that's a circle to the right, just as it is. What we're doing is taking all of the r values that we would have gotten from cosine theta, we would take all those answers and then just multiply them by 2. Over here, what we would do is take all the answers that we get from sine theta, take all of those answers for r, but then make them their opposite. All right, so go ahead and predict what you think these graphs are going to look like, and then I'm going to graph them in the calculator. Once we have those images, we can then draw them on the graphs that we already had using sine and cosine. All right, so the graph that I'm looking at right now is the r equals cosine theta graph. And the graph that I want to compare it to is 2 cosine theta, okay? So let's go ahead and take this one out. We don't need that. And then what I'll do, here, I'll type them in next to each other. That way we get to see both of them. Not that it'll probably be that important. All right, let's see what it does. All right, what we end up doing is getting a graph that is twice as big as the one that we had. Well, area-wise, it's actually not twice as big. But what we're going to see here is that the diameter is twice as big. So the center point for this is actually going to be right there, which is here. Okay, so by doing 2 cosine theta, what we have actually done is doubled all the outputs. Okay, so if something was a distance of 1 away from the origin, we're actually going to get a distance up to 2. So let's see if I can get these lined up pretty good. All right, the real test here is going to be whether or not I make contact with that spot, but we'll see what happens. That's pretty good. All right, so that graph is going to be r equals 2 cosine theta. Actually just doubles the diameter or doubles the radius that we have here. All right, so recall that this is the graph of r equals sine theta. Okay, and what we want to look at is r equals negative sine theta. Okay, so let's add these in. We got sine theta. Clear that one just so we see, okay, there it is. And then we are going to do negative sine theta and see that what we get is a flip of the graph. It's actually going to flip over the, what would be like an x-axis here. All right, so the center is still going to be, the size hasn't changed, right? It just flipped everything over, so the center is going to be at that 2.5. And these little graphs are hard to do, but I'll see if I can make it look good. Yeah, it looks pretty good. Matches up on each of those 2 points. So that will be r equals negative sine theta. So negative is going to flip it over a certain axis. You could imagine that the cosine graph will flip from the right to the left as well. All right. In this video, I am not going to be showing you all the different types of polar graphs that we have. However, I am going to be showing you one more of the classic curves that we have. The classic curves include circles, limosons, cardioids, roses, lemniskis, and spirals. Okay, those are the classic versions of the polar curves that we have. So today we are going to take a look at the limoson. We're going to see what that one looks like. All right, a limoson curve is of the form r equals a plus or minus b sine theta, or r equals a plus or minus b cosine theta. Okay, so the difference between this and the circle, at least when you look at the equations, is that you have this extra piece in the front that you would have there. So we did see that if you just got a factor to either the cosine or the sine, that would enlarge the circles, or I guess if you had a fractional number, then it would compress it. All right, so we have this extra little piece here, which does significantly change the picture, and you get a different shape. All right, there are a lot of different versions of limoson curves. There's a bunch of different versions of them, and those versions are really going to be based on the comparison of the size of the A and the B. That would be like the absolute value of those. So if you have, like in this case here, you're going to have an A value which is less than the B value. Don't worry about the minus part here, but because the A value is less than the B value, you're going to get a certain type of a limoson curve. Okay, and then if you were to switch those, the 2 and the 1, you actually get a different type of that curve. Once again, what I've done is went ahead and provided a table of values that fits the equation that we have here. Okay, so all we're going to need to do is just plot these points. You're going to use your thetas and your radius. You're going to plot the points, and then we're going to hope to see some sort of a nice curve that we could build out of those points. But of course, I'll put it into the calculator so you can see the picture that the calculator generates for it. All right, so let's go ahead and start this off. When theta is 0, the r value is -1. All right, so at theta 0, the r value is -1. So we're actually going to go backwards. We're going to start here. That'll be our first point. All right, pi over 6. Pi over 6 is going to be right here. Pi over 6 is right there. And that is going to be at -0.7. All right, so if I'm at that line, I really need to follow it like through, right? So I'm looking at that line, going to be looking at that line, and it's -0.7, and these are going by like 2/10 at a time, so 2, 4, 6. This would be 8, so 0.7 is going to be right there. That actually isn't too bad to plot. All right, at pi over 4, okay, so pi over 4 is going to be at that line right there, pi over 4. we're going to go backwards 4/10. Okay, so match that up. It's right in the middle, so right in the middle line there. That is going to be 2 circles out. Get that line in there. All right, so far we got this point, we've got that point, we've got that point, and that's where we're going. Pi over 3. It really doesn't matter where pi over 3 is because it's going to end up being 0. Okay, so we're at that spot, but that is pi over 3. Next, pi over 2. All right, so at here, we're going to be at 1. Okay, so that's a bit of a jump, right? You get dot, 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 dot. You have a jump that shows up right there. You have a jump there. 2 pi over 3, 2/3 of a pi. There it is. You can kind of see in the background there. That's 2 pi over 3. That will be a positive number, so this is going to be a little bit easier to graph now. We're going to be at 2, so dot, 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 dot. Next, 3 pi over 4. 3 pi over 4 is going to be at that diagonal here, and that will have 2.4. All right, so we're a little bit further out, 2 rings out because that'll be 2.2. This would be 2.4. Be there. All right, 5 pi over 6. We can see 5 pi over 6 right there. 2.7. We're actually getting further out here. 2, 4, 6. That'd be 8. So 7 is sitting right there. 2.7 is in that spot. And then at pi, you're going to get 3. All right. Now, this is not going to complete the graph. There's actually more to it. But at some point, we've plotted enough points. Let's just see what ends up happening. All right, so we got a dot that would connect to that dot, connect to this one, connect to that, connect to that, connect to that, connect, connect, connect. I think right now, if you look at it as like a curved graph, it would sort of look like a spiral, except it seems to bend a bit much like in this direction if we try and follow like a true spiral with this. All right, so let's see what it actually looks like, at least completed. The full period is actually going to be 2 pi. Just so you know, we've only done 1 pi. But if we do 2 pi, we'll get a complete picture for this guy. All right, so let's go ahead and take a look at what the calculator would show us. Okay, and I think I've got all my settings here right. All right, we're going to have r equals 1 minus 2 cosine theta. All right, now let's think about what we saw. We start at this dot, that dot, that dot, that dot. Then it's moving in this direction. See if it graphs it that way. And it did. All right, so it did not actually create a spiral. Okay, it seemed like it sort of did, and then it actually closes back in. It closes back in and then gets back to the start spot that we have. All right, so that is a graph of a limousin. All right, so what we'll do is we'll go ahead and maybe I should keep this on the screen here so that I can do a little bit of a comparison as I draw it. All right, so we got a curve that goes to here. It actually goes through it, kind of hooking back at the 1. Once you get there, I might be messing up some of these points. Maybe it's easier if I go this direction. We got that. These are going to be a little bit hard to draw. Yeah, so I probably missed the curvature. That would be right here. There's not much of one. It comes around. Yeah, that'll look better. All right, and then the rest of it is, it's sort of just like flip-flopped, right? So you could go to 5 pi over 6 and match up to 7 pi over 6 out here. Okay, so if you did a full 2 pi, you'd get all those values that you can plot, but I think we can see that on the graph, this is symmetric vertically, and that'll complete it. All right, so again, this is a limousin. This graph in particular is called a limousin with an inner loop because it has that extra little ring that sits inside of it there. All right, so what I want to do here last is just show you a bunch of pictures, a bunch of different pictures of limousins that you could get depending on the sizes of the A's and the B's. So the one that we had was called an inner loop. That happens if the A value is less than the B value. Okay, so remember the one we did was this. So the A value is 1, the B value is 2, so we had A is less than B. So that'll give you an inner loop. All right, now depending on how the equations are actually set up, you could have a cosine or you could have a sine. In addition to that, you can either have adding or subtracting. Okay, you can have either of those two things, and based off of those combinations, with the A value still being less than the B value, you get these different orientations of the graph. So you could have that. All right, another way that we can compare the A and B If the A is greater than the B, but less than twice the value of the B, you get what is called a dimpled lemma sum. Okay, and that's what these roughly look like here. Seems like it has a little bump on the side of it, a little dent. It's called the dimple. All right, and then another one that's really popular is the cardioid. The cardioid is when the A is equal to the B. And again, you can either have cosine or sine, and you can either have addition or subtraction. So depending on what you've got there, you get a different orientation for the graph. And of course, the same thing was true for the dimpled one here. You could have cosine, you could have the sine, you could either have adding or subtracting, and then it just moves the picture to different locations.
Later, blah.